Right, so welcome to the IMA's Yorkshire branch's event for our November event. Sorry, my brain is fried. It's been a fun day. So we are delighted to have Bryony joining us to give a talk. Keith, would you like to do the introduction, given that you invited Bryony?
Yeah, so he's one of my...
You'll want to come up. See, I could just talk, but basically I'd be parroting. So given that Keith invited, I'm going to hand over to him.
So Bryony is one of my fantastic former colleagues from down the road at University of Sheffield, and I think this is a really exciting application of statistics, which is about archaeology, so applying Bayesian stats to archaeology. And Bryony's the expert, so I'll let her take over from now.
Thank you. Yeah, thanks for your patience with me getting a little bit lost. Okay, so it's on. There we are. I'm talking today. I've called my talk "An Archaeologist, a Statistician, and a Computer Scientist Walk into a Bar." And basically, the meaning behind the title is that's kind of how I envisioned my PhD being sort of formed. It's a really it was a really interdisciplinary PhD. So I originally started by doing a mathematics undergrad, and this is basically where my maths undergrad took me. So this was me excavating at Lowham in Somerset. It was sort of an old Roman villa and the surrounds. And this was basically me just learning how all the data was collected. But the talk that I'm going to give today is just basically going to chat a little bit about the sort of hidden statistics behind radiocarbon dating and chronology construction at excavations in general. So when I mention chronology construction, what I mean by this is that when we're excavating a site, the main goal is to approximate some sort of chronology of human activity at that site. That's what archaeologists are always aiming to do ultimately. And they have a wealth of data that they collect while they're doing this. It's broadly split into two categories. There's absolute dating evidence. This usually comes from scientific dating, so samples which are then radiocarbon dated, for example. And then there's also relative dating evidence, and I'll talk a little bit later about what that looks like. And in my research specifically, I focus on radiocarbon dating, and I'll explain later why not only is the combination of these two different types of evidence interesting, but radiocarbon dating itself presents an interesting statistical problem. So I'm going to give like a quick recap on radiocarbon dating, just in case anybody hasn't, heard of it for a while, just to give a bit of background. But I'm sure most of you know that we have isotopes that we're surrounded by, and a lot of them are unstable. So due to this excess energy stored in the nucleus, and they emit they are radioactive, and they decay over time. So carbon in particular has three isotopes, 12, 13, and 14. Carbon 14 is the interesting one, in my opinion, because this is the one that's radioactive. So we've got the formula. This is usually what people think of when they think of radiocarbon dating, right? They think this is the whole picture. So we've got our number of atoms in a sample, which we might measure. And then you've got the number of carbon 14 atoms at some time t equals 0. And then the decay constant, which we work out based on the half-life, which is t half, and then natural log of 2 divided by that. So radiocarbon dating was made possible because Willard Libby realized that living things absorb carbon, and it sort of absorbs it and interacts with the atmosphere all throughout its life, and then it stops doing that as organisms die. So as soon as they die, they stop doing this absorption and interaction with the atmosphere, and then the carbon 14 starts to decay, and we're able to then measure that using the law of radioactive decay. So as you can imagine, this was a huge deal. Archaeologists were thrilled. It won Willard Libby his Nobel Prize for chemistry for this work. But to do this, we need to measure the number of carbon 14 atoms in the sample now. We also need to know what it was at time t equals 0 to get that other measurement that we need. Now, to do it now, that's okay. We can use, historically beta counting was used, and now there's slightly more accurate methods such as accelerator mass spectrometry. So they provide pretty accurate measurement of the sort of concentration of radiocarbon in a sample now. And these measurements are given as an x plus or minus sigma, where you've got some laboratory error. So those errors are much, much smaller now with AMS. But we also require this N0 measurement. And so Willard Libby suggested, well, as long as we can look at what the carbon-14 concentrations are in a living thing now, that would represent what the concentration would have been of the same living thing sort of 10, 15,000 years ago, for example. That assumes that the radiocarbon-14 concentration in the atmosphere and in the biosphere, so sort of the parts on Earth where living things exist, is constant over time, and he assumed that. We also have Willard Libby's half-life that he estimated, which was 5,568 plus or minus 30. So this is what he suggested to be able to radiocarbon date organic samples. Now, he was really wrong about the constant radiocarbon in the atmosphere and biosphere over time. That's okay, because statisticians come in to save the day later on, spoiler. His half-life also isn't super accurate. That's not the end of the world, because you can make an adjustment for that, because it's just one value that's wrong, and it's wrong for all. It's wrong for all values. So the second one's not so much of a problem. The first one, huge problem, and we need to do something about it. So we essentially needed a function to convert what we would call radiocarbon measurements to the calendar scale. Now, in an ideal world, there would be some deterministic function that we could use for that, and it would just be a straight conversion, and there'd be no problem with that. However, that's not the case, hence the statisticians coming in. So what we do instead, and I say we, not myself, there's an international team that work on this, but they take data and use continually updating curve fitting methods to approximate this calibration curve. I'm going to talk a little bit about that now, but I won't focus on it too much, just because that's not the area of research that I focus on. But if anyone's interested, Paula Reimer and her team have lots of papers all about the calibration curve and how they model them. So in terms of roughly, crudely how it's constructed, there's lots of different sources of data, but a really common source is dendrochronology dates. So using tree ring dating to date an organic sample, a tree, and then you can also get a radiocarbon date for that. And what that gives you is a fairly accurate, usually to 1 year from dendrochronology calendar year, that you can map to a radiocarbon year with an error. So then that can be used as the data, which we then use to construct the calibration curve. For older dates, they have to get slightly more imaginative with the dates that they're using. But as I said, that's detailed in Paula's papers and is continually being updated all the time. So you can imagine we've got these 2 dates that we can use, and then they are used to form calibration curves. So initially, researchers would use their own local calibration curves, and everyone was just kind of going and doing whatever they wanted, basically. And eventually, thankfully, the community said, we need something that's internationally agreed, so that when we are using radiocarbon dates and we are interpreting them in our findings from excavations, that they're consistent and comparable to other projects. So now we do have this international working group. So this is INCAL, who have been working on modelling and revising every 5 years or so. I think the most recent one took a little bit longer, but the most recent one was INCAL 20. So there's colleagues at Sheffield who still work on this and have historically worked on it, and other colleagues that have left Sheffield and gone on to Leeds who are still working on it as well. But it's had a home at Sheffield for a while now. So for each of values of theta, so thetas are your calendar years. So for every calendar year, we have a corresponding mu theta. That's a radiocarbon year. And then we also have an error associated with it. And that is just because within the data that we've used to construct the calibration curve, we have error in the radiocarbon dates. So we have to have an error, therefore, in the curve as well. That error also accounts then for the uncertainty in the curve fitting methods that are used to produce the curve. So this is what the curve looks like. So some slight problems, of course. So this is great. It means we can calibrate, but I hope you'd notice that that is not a one-to-one relationship. For example, if I wanted to try and calibrate 5,300, I've got 5 potential dates there just from the curve itself, not even accounting for the error. So it causes a bit of a problem in the sense that we don't have this one-to-one relationship. which is fine. We solve that a little bit later, and I'll show you what we do, but it's definitely not a one-to-one relationship, and you can see how much it sort of varies over time. So Willard Libby's initial assumptions were a little bit off, even though the initial idea of radiocarbon dating was brilliant. So before I go on to sort of talking about how we construct the model, just a quick reminder of the notation. So for a given radiocarbon date estimate, so this is nothing to do with the curve now, this is a sample, and I've got an estimate, and I've managed to get from the lab. This is estimated to be X radiocarbon years old, plus or minus some error, sigma. And this sample will have a true calendar date theta. That's the goal, that's what we're trying to estimate. And then we're going to calibrate that using the calibration curve. And we've got the mu, which is the curve itself, and then the delta, which is the error on the curve that we have to account for. So when we calibrate them, you can see that it takes this nice normal distribution, which we assume for the radiocarbon age that's provided by the lab, and it becomes this less useful multimodal distribution that archaeologists understandably really don't like, because for one, I can't give them an estimate with an error for that, and it's much wider than the initial estimates as well. Say, for example, they're trying to say that this bone belonged to that king, and I say, well, it could be within this 300-year period. That's hugely unhelpful for them, especially because they've got so much extra information that they obtain from the site. So it makes sense that we take this, we take that other information, and we combine it together. So we sort of solved one problem in terms of the calibration. We are able now to calibrate these radiocarbon dates, but then we have another problem in the sense that we have these wider intervals, and we also are still not including this extra information that we can obtain on site. Now, the extra prior information that they might includes something called stratigraphy. I'd never heard of it before I came into this research, but essentially what it is it's just the practice of looking at the order of the samples that they're found in the ground, so how deep down they are, and it's inferred that the deeper down a sample is found, the older it is, just sort of by how matter sort of geographically builds on top of the other. Now that obviously that's not always the case. For example, if something's been dug up and something's been popped in and then something on top, but archaeologists are really good at knowing what's happened based on what they can see in terms of cuts in the ground and changes in soil colour and density and things like that. I'm not going to lie, when I excavated, I couldn't really tell the difference in the layers in the soil. They'd point them out to me and I would just nod and go, yes. But I'm sure it was correct. It was just very wet. It was windy. It was November. It all just sort of looked brown. But they know the difference between the soil, and then they can make a note on which different layer samples have been found within that. And that gives us some order into those dates, which then sort of constrains these really wide probability distributions that we have after calibration. So this is a really crude drawing of a site that you might see. So for example, if I found that skull in layer 6, I would infer that that's much older than the axe in layer 5, and I could date that by using the wooden handle and dating that because it's organic matter. And then the bone shard in layer 4 would be the youngest sample here. And you can see that number 2, that's cut into the soil, and then you can infer that 1 and 3 are equivalent to each other based on the fact that they're the same soil that's been cut into. So it's this kind of information that it's a very simplistic version, but that's the kind of information that they will obtain while they're excavating. So typically this is represented by archaeologists using something called a Harris matrix. So this really confused me when I first started doing this research, because I was looking in a paper for a matrix, as in like a mathematical matrix. And I was like, where is this matrix that they are talking about? And I finally realized they meant this diagram. But yes, so all it is just boxes representing the layers and the cuts into those layers, and then the edges represent the relationships between them. And they often use these double lines to then represent equalities between layers of soil. Now, as a human looking at this is fine, this makes sense. However, if you had a really large site and you wanted to put this into a computer and say make it into a mathematical graph, which as a mathematician, if I'm looking at this, intuitively that looks like a mathematical graph to me, the computer's going to interpret that as me saying that 1 is older than 3, which is older than 1, which doesn't make sense. So intuitively, these don't translate straight away to a mathematical graph. So part of the research that I focused on during my PhD was trying to convert these Harris matrices to graphs and then build software that can handle them in a way that can then help us build these statistical models slightly more automatically. So really easy solution. They're both representing the same point in time. I'm just going to make them the same node. To me, that's a parameter I'm trying to estimate. So that's the same date in time. It's the same parameter. So nice, simple option. The archaeologists mostly like it. I think they like the idea of having a Harris matrix option, which I'm going to hopefully put into the software at some point, but they're okay with the fact that this is how we're representing it in the software that I built as part of my PhD. So Bayesian inference, I'm sure most of you are really familiar with it, but on the off chance that we've got some sort of hardcore frequentists in the audience anywhere, I thought I'd pop it up. So the basic idea, very oversimplified again, like the stratigraphy, the basic idea is that if you've got prior information that you can represent as your prior, and then you multiply that by the likelihood, which you obtain from the data, you obtain something that's proportional to your posterior, which is your best posterior estimate for your true value of some parameter that you want to approximate. And in my case, that's the true calendar age of any given sample. So in my case, the expert knowledge comes from the stratigraphy. Later in the talk, I'll mention a little bit more expert knowledge that we also use as well. The data comes from radiocarbon determinations, but there are other scientific dating methods as well that the data could come from, and we're hoping eventually to extend my research to those other scientific dates as well. They just don't have the calibration step, and I think that's a little bit more interesting just from a stats point of view. So that's where we focused. And so the output is a candidate estimate that is hopefully as accurate as it can possibly be based on all the information on the site. So I mentioned earlier that we have this problem about this one-to-one relationship that we don't have when we're trying to calibrate these dates. But that's fine because all we do is we represent our likelihood here, as you can see, as a normal distribution, and we do all of the calculations on the radiocarbon scale because it is one-to-one, go from the calendar back to the radiocarbon. It's just not the other way. So what we do is it's assumed that each radiocarbon date has a true mean of mu theta I. So that is our true theta I is our true calendar age for that sample. And so then if we calibrate that back to the radiocarbon scale, that would be its true radiocarbon age. And then it has some error that comes from it being dated by the lab. So if we convert everything back to the radiocarbon scale, we're able to plug in each possible theta that we think that a sample could take and work out a probability for each of those values of theta, and then you get a likelihood. So what initially seems like a difficult problem because there's lack of one-to-one relationship is fine because we can get probabilities or likelihoods for each of the thetas based on converting it back to the radiocarbon scale and calculating those probabilities on that scale. So that's how we do that. So again, we've got delta, that's just the error from the calibration curve. Sigma is the error from our sample from the lab. Two sources of error there. And then your xi is the estimate that is given to you by the lab for that particular sample. So if you've got multiple dates that you want to approximate the true calendar ages for, it's nice and easy. They're just treated as independent distributions, and then you just take the product of them all, and that gets you your joint likelihood that you need. Okay, so the prior knowledge. The prior knowledge is even easier to represent, causes problems though for them when you want to calculate your posterior. So really simple. If the dates themselves satisfy the ordering that the archaeologist has told me that it needs to satisfy, then we have a probability of 1, and otherwise we have a probability of 0. So instinctively, that's super, super simple, except that's not easy to then analytically derive a posterior for, but that's fine because MTMT comes and saves the day, essentially. But our posterior for a really sort of basic model where all we've got is radiocarbon dates and stratigraphy would look like this. So you've got the product of all the individual likelihoods for all the individual dates that you're trying to obtain true calendar ages for, and then the indicator function, which constrains them to having that specific ordering that the archaeologist has told us they need to have. So a simple example, because at the moment that's just a lot of sort of formulae, is suppose we've got 3 layers on the excavation. So going back to that picture I had before where I had the skull and the axe and the bone fragment, and they've each got individual dates. So the School, for example, might be 900 plus or minus 50, and so on and so forth. I'm actually just going to quickly go back just to mention something. So the scale that these are on is a little bit important in the sense that they're in before present and then calendar years before present. So they're larger, the larger the number is, the older it is. So it's different to how we normally think about dates. Present is taken to be 1950. I think partially because a lot of the atom bomb testing that came after that, but also just because you need a fixed date, and that's the one that they chose. So the larger the number is, the older the date is on scale that we're working in. Okay, so here we've got our prior knowledge. It tells us that theta1 is older than theta2 is older than theta3. And that'd be what would go in my indicator function. Now, this is a simple example without ordering. These are what they look like when they're calibrated. So very multimodal and very wide as well. And then this is what they look like with ordering, which is not massively different, given that there is only 3 dates. But if we just sort of plot them over each other, you can see that we do have slightly more peaks in different places. And at a given site, you're likely to have way more than 3 dates. So quite quickly, these constrain them, and you can reduce these by hundreds of years, which is really helpful. There's also more information that we can include as well, which I'm going to talk about. So group to the model. So archaeologists tend to group what we call context. So context are those layers of soil or cuts into the soil, and they can group contexts into what they typically call phases. For example, if you've got lots of samples that you found that are clearly indicative of a particular settlement, and then it's very clear, say from the cultural findings that they found, such as the pottery and things like that, that earlier up, this is a different settlement, they would then be able to say, we'll group the first lot that we found into this group and the second lot into this group based on, say, if it was sort of Roman pottery, and then later on you found some sort of context that made you think it was Norman, for example, they'd be able to then group it based on that information. So that grouping is helpful because it allows us to imply sort of additional constraints within the model. So we denote the start and the end of these groups as alpha and beta. So we have each individual group J would have a start date alpha J and an end date beta J. And then each of the individual groups will have NJ context within that group. And you can have lots of different relationships between these groups as well. So we can say that they are abutting each other, so directly after each other. We could say that there's a gap between these two groups. There's sort of a bit of time where it's implied that there's sort of no occupation of the site, or it might be that there's overlapping. So I guess maybe like a Viking raid, for example. I'm not entirely sure. I'm definitely not an archaeologist or a historian, but they're able to infer this information, and then they can tell me that, and that tells me how my alphas and betas should be ordered within themselves within the model as well. So now we've got 3 sets of parameters that we want to estimate. We want to estimate our thetas. That's our set of true calendar ages for all the samples we've got on the site. We've then got all of our alphas. That's the start of all of our individual groups / phases. It's used interchangeably. And then beta is the set of all the end calendar dates of all those phases. And the goal is to basically get these as accurate as we possibly can. We don't tend to have any dating evidence for the alphas and the betas. These are sort of constructs that the archaeologists are imposing on the model, but they're not physical layers, for example, that we're finding at the site and excavating. So this has a hierarchical component to the model. We essentially assume that for any given calendar age within that phase, we have no prior knowledge about where it lies within that phase. And it could be possible to, incorporate some prior knowledge. There might be, for example, some information that makes you think that there's not much chance of activity at the start of a phase, but then actually more people come along and there's much more chance of the activity being sort of in the middle, and then it might peter off, for example. But typically, archaeologists don't have enough information from what they find in the ground, and so it's assumed to be uniformly distributed between these start and end dates. So then we've got this extra component now within the model, so we're sort of slowly building it up. We've still got that likelihood as before. It's now just got slightly more complicated notation because it's IJ notation. We've then got the normal distribution included in there as well for all of our different phases. And again, we just take the product of each of those for each of the individual phases. And then now we've got this large model. Now, we assume an uninformative prior on our alphas and betas. So we assume we have no knowledge about the distribution of these alphas and betas at all.
Questions at the end.
I'm happy to answer them now.
Okay, so someone just hand roots of days, disjoint contiguous.
The calendar, as in, well, it depends on what the archaeologist implies. So that will then be incorporated within this indicator function here. So this has all the orderings of all the different parameters, and depending on what the archaeologist tells us, that is how we'll set it up within the model. And part of my research during my PhD was to try and set up a piece of software that would essentially take the information that they're giving us from their Excel spreadsheets and build that MCMC model automatically. So sort of build that ordering from the information that they're giving, which ends up with lots of different combinations because of how many different sort of options there are. But it was a fun puzzle. Yeah, no, happy to answer any questions along the way. Cool. Okay, so again, we sort of made an assumption here and accidentally made a mistake in the assumption, and that is assuming this uninformative prior on alpha and beta doesn't cause any problems. So Nichols and Jones, way back in 2001, realized that, because this, I'm sorry if it's going to make any of you guys feel old, this model is as old as me. So in 1996, this model first came out, and then 5 years later, Nichols and Jones realized that actually we've got a few issues here, essentially, in the sense of having this uniform prior on the alpha and beta. So it works well for estimating theta in the sense that it doesn't impose anything we don't want to, except it has an adverse effect on the phase boundaries. And what it essentially does is it sort of forces them to spread out a little bit more than we want to. And the reason for this is because while we're taking this to say that we have no prior knowledge about alphas and betas individually, which most of you will know this is known as an uninformative prior, it has a sort of adverse effect on the span of that particular group. So if we assume that the span of the whole chronology, for example, S, so that's the alpha of your very oldest date, take away the beta of your very youngest date, so a span of all plausible dates within our chronology. So that might be determined by an archaeologist based on their evidence, or we could just take it to be the whole calibration curve. But if we then try and work out what we think the span of our particular chronology is, based on the model we set up now, that is not sort of proportional to 1, which we would expect it to be, because we have no prior knowledge on how long we think this chronology is. But what it accidentally does is if we work out the marginal posterior for this span, it ends up being this. So it ends up being R minus S divided by 2 to the S to the 2 minus M. And M is your number of group parameters. So the more parameters you've got, the more of a problem this causes as well. So it means that a span of sort of 2S is favoured over S by a factor of around 30. And that's definitely quite strong prior knowledge that we're accidentally imposing that we definitely don't want to do. So there's more information in the Nichols and Jones paper about this and how they derived it. But it does mean that actually we want to impose a slightly different prior on our alphas and betas, which will then doesn't have any effect on the thetas, but it does then sort out this issue of sort of having this stretching effect on the alphas and betas. So then we impose that in there as well. And just to show you sort of how this works, so this is the Shag River mouth in New Zealand. So this is work on an excavation out there. And this was an estimate for the very uppermost phase boundary on this site. So when we set this to be an uninformative prior on alpha and beta, we can see that sort of the estimates go from around sort of 650 years to almost 1,000 years that they think this span is based on this uninformative prior. But then when we include this adjustment that Nichols and Jones suggested, actually there's hardly any probability of this sort of larger span at all. And we actually think it's more likely to be around the sort of 700, 600 mark, which makes a big difference in terms of, again, if we're thinking about human lifespans, which archaeologists are working in, that makes a big difference in terms of the interpretation of a site that we're going to make. This is, oh, sorry, I beg your pardon. This is for the actual estimate of the sample. So it shifts where it is, sorry. And then this is for the phase length. So they thought initially it was 400 years to sort of 0 were all plausible dates. And actually it was deemed that a much shorter length is most probable. And actually anything over 200 is really unlikely. for those, so that this is where taking away the difference between the very oldest, so the alpha, very oldest alpha, and the very youngest beta. Okay, so where next? Nicol and Jones sort of solved it in 2001. So what else? What other problems do we have? Archaeologists don't always agree. In fact, there were some interesting papers of archaeologists sort of arguing with each other on interpretations of sites that I got to read during my PhD, but they may provide differing prior knowledge of what they believe to be the true prior knowledge of a site. And due to poor model selection options, essentially what they do is they just pick a model and pretend that that's the exact right model, and they truly, truly believe that. Another problem is that these models that we try and build are often built by hand. So they are sort of worked out on paper and then coded into a computer or into existing software, but it has to be done individually for each model. So you can see why they don't want to do this for multiple models, because they just don't have the time. And archaeologists are very short on money and time, and so they just have to do the best with what they've got. But on the other hand, by excavating, you're destroying your data. You can only collect it once. So it's important to make sure that we are getting the most from this data, and that we are not just assuming one model, publishing that, and that is what's archived, and all of this additional data sort of along the sort of statistical analysis process that is happening before you have this publication is lost. So this is what we wanted to avoid by building software that can manage this data, build multiple models, and archive all of the data produced sort of along the way automatically, or at least semi-automatically, at no cost to the archaeologists. So that was fundamentally the goal of the PhD, was to provide a proof of concept of that. So this is an example of sort of a really big Harris matrix, and you can see they've just printed it out. It's on the floor. They're working through it bit by bit, and then they would have to then put this into software rather than taking the above-below relationships and the grouping from Excel spreadsheets that you'd obtain on site and have something just build it for you. So it takes a lot of time and a lot of energy to do this. So as I mentioned, I wanted to try and build some software to sort of at least proof of concept to show that we could automate part of this process. And then could we include any way of assessing the suitability of these models? So this work started way back in 2015. So Tom Dye is our collaborator out in Honolulu, and Professor Caitlin Buck is over in our department up at Uni of, and she's been working. She originally worked on the INCAL, working in the INCAL working group, and then moved into this more sort of Bayesian chronology construction area as part of her work that followed on from her own PhD back in 1996. And they were the ones who initially first suggested using directed acyclic graphs, and that's sort of what formed the funding application for my PhD. So we were hoping by representing this information as these directed acyclic graphs, that would allow us to automate it. And then therefore, could we build multiple models if we could take the information from those graphs, build the MCMC algorithms to approximate these posteriors, and obtain this output without the user having to sort of manually encode it. So here's an example of multiple priors. So here we've got an alpha and a beta of a particular phase, and we've got 5 samples in between. So one expert suggested that they think that these are all contained within this phase, and they believe this information is strictly true. So they would want in their model that alpha would be older than all of the thetas, which would then, all those thetas would be older than the beta. And that's quite easy to code in. Another expert disagreed. They said that they believed that theta 31 was definitely constrained within that, but they weren't sure that all of the other samples were definitely contained within that grouping. They were sure that they were at least older than the end of that phase. They had to come before the end of that phase, but they weren't sure if they'd sort of moved within the ground and had accidentally ended up in a younger group. And so they weren't confident enough to say, we want all of these to be constrained by that alpha, but they did want to be constrained by the beta. And it does make a difference in terms of the results you obtain. And I think it is an interesting sort of statistical problem to have that, look at those 2 models and to have that archived as well, again, because of this sort of excavation is destruction concept of we cannot obtain this data again. So both sort of published papers saying that they, I think this is right, but couldn't agree. Now, that was a really simplistic version. This is typically sort of a bit more indicative of the kind of thing I'd be working on. So at the moment, I'm working on one on, it's sort of an excavation from the Llama River Valley in Ecuador. And I think that has about 140 odd contexts at the moment. So it looks a bit more like this. And so you can imagine that there's lots of different then plausible models that we could possibly have and problems that we could encounter if we're then just ignoring uncertainties about these relationships. So the dilemma is, I built the software, we can build these multiple models. It does work for the case studies that I tested it on. And we can build lots more using these graph theory algorithms that make it really easy to add and remove nodes and edges. But then how do we decide which models are the best models? Can we decide that? How do we sort of measure that? So what do we do with the results that we get? Before I get you excited, I still don't have an answer to this. This is something that is still sort of ongoing work, but I thought I'd chat a little bit about it just because I think it's an interesting statistical problem. So some obvious choices are sort of sensitivity analysis, model choice, model averaging, or posterior belief assessment. So I'm going to chat through sort of how I worked through these and decided which ones to focus on. So sensitivity analysis is used, and I think it is really important when doing chronology construction using Bayesian methods. And it essentially looks at how sensitive the model is to particular dates being included or not included in the model. But I think all that tells us is, do we have potential outliers within our sort of data? It doesn't really quantify how confident one is in the model or how confident sort of we should be. And for large and complex models, it's not clear how to do this sort of reliably with the existing software we have. Model choice, this is something that's also done in existing software where people automatically encode models one by one. They typically use these agreement indices, which are basically sort of adjustment to base factors. And so they just compare the likelihoods of the data samples with the posteriors under a sort of range of models, and they give these agreements. Seems a little bit arbitrary, sort of. It's like the whole p-value thing, right? Some people feel like it's a bit arbitrary, other people feel like it's very helpful to have a threshold that you can compare something to. And so some archaeologists really like these because they know that they have a threshold that they will sort of deem a model to be sort of suitable or not. Others feel like it's a little bit arbitrary and don't really trust it as much. So we chose not to use these for our work. Model averaging was something I also looked into but eliminated quite quickly just because it assumes that you have a true model in your ensemble of models, and I absolutely categorically don't believe that ever. We can never fully excavate a site. There's human error. Sometimes they have absolute novices like me on the site helping excavate, so you can imagine there's always going to be that sort of human error. But even if you had a whole team of experts, that's still going to be there. And any sort of further excavation. So the one that I was at in Lowham was a sort of additional excavation after some initial ones in the 1950s. And so you're constantly then able to sort of obtain additional information. And even then you still don't have the true model. So quite quickly sort of ruled that one out. And so then I had a look at this posterior belief assessment. So this was Williamson and Goldstein who sort of worked on this initially, and they claimed it was a methodology that allowed you to sort of you obtain beliefs for your key quantities of interest, but you don't obtain the sort of posteriors themselves. So you work with expectations and variances, and you can use as many alternative forms of priors and likelihoods as you want. So as many as you're prepared to consider, essentially. So we thought it was quite attractive because we've got many models that we wanted to think about, and we didn't want to assume that we have the true model within our set of models. And they'd shown it can work for other applications as well. So we figured we'd give it a go. So I originally did a little bit of work with Daniel Williamson, who was very kind and sort of hosted me towards the end of my PhD. And we looked at how we could try and quantify information that you obtain from the models in terms of expectations and variances, it's something I definitely need to put a little bit more work into, because as you notice, we have these really multimodal distributions. So doing anything in terms of expectations and variances for this kind of problem is a little bit iffy. And so I've been focusing on my software at the moment, but then once that's finished, it would be good to then pick that work back up and do a little bit more work in terms of looking into, can we utilize this, or actually has it moved on, because it has been 3 years since I finished my PhD and there might be better options out there that I can investigate. So that was sort of what I looked into towards the end of my PhD, but sort of ran out of time and had to quickly write up before I ran out of my 4 years. So post-PhD progress, I'm actually a teaching only member of staff up at the university. So any research I do is either in my own time or whenever I can try and get some funding from various pots within the university or externally. So over the sort of past 3 years, I've managed to get 3 months worth of time for a research software engineer to work on the software, which I ended up calling Polychron for multiple chronological models. This was brilliant because I'm not a software engineer, so the code was functional but not pretty, and it was really nice to have someone who actually knew what they were doing, and they were able to refactor the code and get it sort of packaged ready to be released in Python. And then we also had a undergraduate intern working with us this summer, so they worked with myself and the RSC, and he mainly worked on sort of testing the changes that we'd made and making sure that the software still works. It was also really handy because he had a Mac, so he was able to test, see if it works for users on Mac as well. And then we've just obtained 150 hours funding for that same intern to carry on working on it part-time throughout the semester. So hopefully he can continue this work as well. So this is the intern, Shreyan. He did a fantastic job. So he was funded by the NA. So if any of you guys have software that within your research and want to obtain funding to sort of have interns working on this, the NA have a lot of funding. And it might be worth looking into whether you guys can get in on that, because it's northern universities that are all sort of together. So they were able to fund him working on this, and this was him presenting at his first ever conference, and he did a fantastic job. But this led to the first Python package release. We're hoping to get a short software paper out of it, which Ryan will be an author on as well, and hopefully more to come in the future after that. So thanks for listening. If you have any sort of feedback, ideas or questions, especially on the model selection side of things, I'd love to hear about it. Feel free to drop me an email, and that is the GitHub if you're particularly interested in the software side of things as well. But yeah, thank you. And that's the bibliography, in case anyone's interested.
Yes, perfect. Right, I'll go back to hosting duties. Okay. Does anyone online or in the room have questions? Rosie, are you all right just to keep an eye on my laptop because I'm logged into the chat in case anyone pops it on the chat? On the silence.
No questions, just some.
He's got one. Go on.
So, can you just make sure to repeat the question?
Yes.
So one thing I was wondering is like when you like do posterior inference using MCMC, I always think that takes a long time to do and is like, to fine tune as well. So how computationally efficient was your MCMC algorithm, and how easy was that to do?
Are you okay to repeat it?
Yeah. So Keith was asking how computationally efficient the MCMC algorithm is. It could definitely be improved. I will say that for sure. So what I basically followed Nichols and Jones's algorithm, which it samples. There's 4 steps to it essentially. It samples a theta, checks if it's going to be accepted. Samples an alpha or a beta, checks if it's going to be accepted, and then it has a scaling step that sort of moves it around the parameter space, and then shifting step, which moves it around the parameter space. And those final 2 steps do improve the efficiency massively. It did help so initially it was really inefficient, but that was partly because of how I programmed it. Even just silly things like in Python, if you sum an array rather than doing the array dot sum, one's much slower than the other. And I say much, it's like fractions of a second. But if you're doing this for say 150 parameters for sort of 50,000 samples for each of those parameters, it really quickly slows it down. So I had loads of fun trying to make my code more efficient. I had really enjoyed that. I was basically doing that to put off writing. But yes, I managed to make it a lot faster, and that now it sort of takes a couple of hours, and I'm kind of okay with that. I've usually got something I can potter around and do while I'm waiting for that. But it is something that in the future I would really like to look into, because that algorithm was suggested in 2001 and MCMC has moved on massively since then. It's just that the main idea at the moment was proof of concept about, can we automate taking that information, building these graphs and then feeding that into the algorithm, which was the main goal.
You had a question, didn't you?
Yeah, so you talked about the radiocarbon calibration curve.
Yeah.
The fact that they get updated every 5 years or so. Can you give a sense of, as they're updated, how much does that throw off kind of previous dating? Does it kind of rewrite things by a large amount? Say something was dated 20 years ago, for example.
So I've not found it to be particularly a problem. I think for more, I say modern samples, sort of 0 to 10,000 years, in that range, it doesn't make a huge difference. I think probably for sort of prehistoric samples, it will make a bit of a difference, because they made leaps and bounds in terms of how they can accurately date sort of these really old samples that they're then using to build the curve. So I would say for older samples, for sure, it definitely makes a difference. I think the main thing that makes a difference in terms of calibration is using the right curve. So I didn't mention this, but there are actually 3 curves that you use. There's the Northern Hemisphere curve, which is called INCAL. There's then the Southern Hemisphere curve, which is SHCAL, and then there's the marine curve, so for any samples found within the ocean. I recently forgot to put the right curve on and then got some really dodgy results and realized that it's because I've not used Southern Hemisphere, recalibrated it, and it was all fine. So they definitely make a difference. It more than, I think, using which year curve you use. But as long as you mention which one you've used, then they're all freely available on the website, and you can obtain the same results again, which is handy.
Does that mean that things decay differently depending on whether you're northern or southern hemisphere?
Yes, yeah. So it's to do with the sort of composition of the soil and how carbon sort of is released and interacts with the atmosphere sort of wherever you are. I also think it makes a difference as well in terms of sort of solar weather and how that impacts where you are sort of on the earth, essentially. So yeah, it's quite interesting, because I didn't think I could understand the marine curve making a massive difference, because water compared to air, but I was really surprised to see how much of a difference the northern versus southern hemisphere made within that. And I'm glad it made a difference, because it meant I spotted I'd used the wrong one, so that was handy.
Is there much data about kind of, so if something's found in a desert compared to forested area and things like that, like, is that going to make a difference? Is anybody looking into that?
So I think, I believe that offsets are included to account for things like that, and that tends to happen before the data comes to me to sort of work with. But yeah, I do believe that offsets are included for sort of extreme situations. But even just sort of on the same site, if it's found in like a peat where it's sort of really damp compared to elsewhere and things like that, they do take that into consideration. It's so cool that the amount of information they can get from just sort of one excavation. I just think it's really cool.
Any other questions? Just give it 10 seconds in case anyone's typing. No one? No? Okay. You've stunned them into silence. Well done.
Hopefully they followed and not rambled for however long.
No, honestly, it was good. Okay, so we'll thank Bryony again. Thank you very much. And we hope, sorry for the technical difficulties. It wouldn't be an online meeting if things didn't go wrong.
Yes.
Yeah.
Sorry for getting lost.
Oh, don't worry about it. I only got here briefly before it started. So.
I've lived here 11 years. I have no excuse.
Perfect. So as I said at the start, there will be another talk by the branch at some point in the new year. We are just finalising the details, so keep your eyes peeled for that. And otherwise, thank you everyone for attending. Excellent. I'll bring the meeting to a close now. Perfect.